In this example, we're analyzing the velocity of a plane. Now, as I discussed in the text, a plane's velocity is influenced by the velocity of the wind. In fact, if you think of the plane flying, in the absence of wind, we could call its velocity v-plane. Well, the actual velocity of a plane flying when there's wind is v-plane plus the velocity of the wind. Well, in this particular example, we're dealing with a plane that is being flown with a velocity of 125 miles per hour at a direction of 30.0 degrees. In the absence of wind, this would be the plane's velocity. However, in the example, there is wind. The wind is blowing at 20.0 miles per hour at a direction of 225 degrees. And the question is, what's the plane's final velocity? Well, as I just discussed, and as is drawn in the text, the final velocity of the plane will be the vector sum of the plane's velocity and the wind's velocity. So in order to compute the vector sum, the first thing we're going to have to do is take both of these vectors, the velocity of the plane and the velocity of the wind, and split them into their x and y components. So let's do that. We'll start with the plane. The x component of the plane's velocity is simply the magnitude of the velocity, 125 miles per hour, times the cosine of the angle, 30.0 degrees. When you work that out, that's 108 miles per hour. The y component of the velocity is the magnitude, once again, 125 miles per hour, times the sine of the angle, 30.0 degrees. When you work that out, you get 62.5 miles per hour. Notice that I have three significant figures for both components because both the magnitude and direction have three significant figures. All right, that's the velocity of the plane, but we also need to take care of the velocity of the wind. Splitting it into its x component involves taking the magnitude, 20.0 miles per hour, and multiplying by the cosine of the angle, 225 degrees. That works out to negative 14.1 miles per hour. To get the y component, we once again take the magnitude, 20.0 miles per hour, and multiply by the sine of the angle, 225 degrees, to once again get negative 14.1 miles per hour. Now, why did we go through all this rigmarole? Well, remember, to add vectors, we can only add their components. So now that I have the x component of the plane and the x component of the wind, I can simply add those together to get the x component of the final velocity. So the x component of the final velocity is simply the x component of the plane, 108 miles per hour, plus the x component of the wind, negative 14.1 miles per hour. That works out to 94 miles per hour. Now remember, in this step we're adding, so the significant figure rules come from addition and subtraction. In addition and subtraction, you look at decimal place. 108 goes out to the ones place, negative 14.1 goes out to the tenths place, so I can only report my answer to the ones place, and that's why I get 94 miles per hour. Okay, now we can get the y component of the final velocity. It's simply the y component of the plane, 62.5 miles per hour, plus the y component of the wind, negative 14.1 miles per hour. That works out to 48.4 miles per hour. I can report this answer to the tenths place because both of my components go out to the tenths place as well. All right then, we now have the x and y components of the plane's final velocity, 94 miles per hour for the x component and 48.4 miles per hour for the y component. Now all we have to do is convert that into magnitude and direction. Well, the magnitude is simply the square root of the square of the x component plus the square of the y component. The x component is 94 miles per hour, the y component is 48.4 miles per hour. We square each of them, add them, and then take the square root to get 106 miles per hour. Now remember, this is like addition, so we look at decimal place. Since 94 goes out to the ones place, our answer can only go out to the ones place as well. Now we have to deal with the direction. The angle is the inverse tangent of the y component over the x component. We know both components, so when we put them over each other, the units cancel. That's good. And when I figure out the inverse tangent of 48.4 divided by 94, I get 27 degrees. All right, now we're not necessarily done, are we? We have to look at the vector and see if that angle is properly defined. Well, to look at the vector, we look at the x component. It's positive. That means it's to the right of the origin. The y component is also positive, so it's above the origin. If it's above and to the right of the origin, It's in quadrant 1 of the Cartesian coordinate plane, and in that quadrant we don't have to do anything to the answer that comes out of our calculator. So the actual properly defined direction is indeed 27 degrees. Thus, the final velocity of this plane is 106 miles per hour at 27 degrees.